In this video, I will explain Newton's second law of motion and its application. Newton's second law of motion states that the force acting on an object is directly proportional to the rate of change of its momentum. And the force acts in the direction of that change. So the force acting on an object is directly proportional to the rates of change of its momentum. P is the momentum, which is the product of mass and velocity. So we have F directly proportional to the rate of change of momentum. Now, F equals to the proportionality constant K multiplied by the rate of change of momentum. Now, the value of K was found to be equal to 1. So we have F equals to over dt. M is the mass, V is the velocity. Now, the mass may or may not be constant, but when it is constant, can bring it out. So F equals to M dv over dt. dv over dt is the rate of change of velocity, and that is acceleration. So we have F equals to ma, since dv over dt is a. So F equals to mass times acceleration. The force is equal to the product of the mass and the acceleration. F is the force in Newton, m is the mass in kilogram, a is the acceleration in meter per second square. This F is the net force. So now, we can make A the subject of the formula here. So A equals to F over m. So the acceleration is inversely proportional to the mass. So for the same force, the higher the mass, the lower the acceleration. Higher the mass, since the acceleration is inversely proportional to mass, so the higher the acceleration, the higher the mass, the lower the acceleration. For example, if this is a mass of 5 kilogram and this is a mass of 2 kilogram, if a force of 20 Newton acts on both masses, so the acceleration of this will be equal to 20 over 5, which is 4 meter per second square. The acceleration of this will be 20 over 2, which is 10 meter per second square. So as you can see, the acceleration of this is more than this. So the lower the mass for the same force, the lower the mass, the higher the acceleration. So it means a light object is easier to speed up than a heavy one when you push them with the same force. The force is 20 Newton for both, but they have different mass, so they have different acceleration. The one with the lower mass has the higher acceleration. So that's for that. F is directly proportional to the rate of change of momentum. So if the mass is constant, F equals to ma, force, mass times acceleration. So the net force is equal to the mass times the acceleration. Acceleration is inversely proportional to mass, which means the higher the mass, the lower the acceleration. So it is easier to accelerate a lighter object than a massive one, because acceleration is inversely proportional to mass for the same force. Here is the question. A 900-gram stone is pushed along a tarmac by a horizontal force of 20 Newton. A frictional force of 8 Newton opposes the motion. What is the acceleration given to the stone? We know that F equals to ma, where F is the net force. So we have to get the net force here. Net force is equal to 20 minus the frictional force. 20 minus 8, and that's 12 Newton. So the mass of the stone is 900 gram. We have to convert it to kilogram by dividing by 1000. So equals to 0.9 kilogram. So F equals to ma. A equals to F over m. That's equal to 12 over 0.9. That's 12 divided by 0.9 is 13.33 meter per second square. So that is the acceleration given to the stone. Find the net force, which is difference between the horizontal force and the frictional force. Then use the formula F equals to ma to get the acceleration. The next thing is impulse and change in momentum. Impulse, denoted by J, is equal to the product of the force and the time the force acts. So J equals to F change in T. F is in Newton, time is in seconds. So the unit of impulse is Newton seconds. Now, for the change in momentum, momentum is product of mass and velocity. So the change in momentum will be the final momentum minus the initial momentum, which is mv minus mu. So that is for the change in momentum. Now, from Newton's second law, F is equal to the rate of change of momentum. So if you cross multiply, F change in T equals to change in P. Since F change in T is impulse, it means the impulse is equal to the change in momentum. So impulse equals to change in momentum. The unit of impulse is Newton seconds. The unit of momentum is kilogram meter per second. So it means Newton seconds is equivalent to or equal to kilogram meter per second. Since impulse is change in momentum, the unit of change in momentum is still the same as the unit of momentum. Now, there's one important thing you need to know about this formula. If this is the impulsive force and this is the time, F is inversely proportional to the time. So it means for a given change in momentum, the force increases when the time taken for the change is short. So if the time taken for the change of momentum is short, then the force is large. And the force decreases when the time is longer. So if the time is longer, the force is small. So it means if the momentum changes very quickly, a large force is produced. But if the same change in momentum happens over a longer time, then the force becomes smaller. So F is inversely proportional to T. If the time is F is large. And if the time is long, then F is small. F inversely proportional to the time. For the same change in momentum. For example, a goalkeeper extends his arm backward when catching a ball to increase the time of impact. Since the ball must come to rest eventually, the change in momentum is the same, but increasing the time taken reduces the force experienced. So the goalkeeper extends his arm when catching the ball. Time increases. So by increasing the stopping time, the goalkeeper reduces the impact force and prevents injury. So by increasing this time, the goalkeeper reduces the impact force. If time increases, the force decreases. So that's the meaning. So by increasing the stopping time, the goalkeeper reduces the impact force and prevents injury. So that's one application of or implication of this. F is inverse proportional to change in T. So take note of that. Let us do one question on this. If a man of mass 80 kilogram jumps from a height of 4 meters onto the ground, calculate the force if he lands barefooted and the landing takes 0.01 seconds. And also calculate the force if he lands with a cushioned or padded shoe such that the landing is delayed to 0.08 seconds. So we want to calculate the force for both cases. The first one is when the man lands barefooted and the landing takes 0.01 seconds. And the second case is when it lands with a cushioned or padded shoe such that the landing is delayed to 0.08 seconds. The first thing is to get the velocity of the man just before landing. The velocity of the man is root 2gh. That's 2 times 9.8 times 4. And that's equal to 8.85 meter per second. Now, the next thing is to get the change in momentum, which is the final momentum minus the initial momentum. The momentum on landing, which is the initial momentum on landing, is equal to the mass multiplied by the velocity. So 80 times 8.85, and that is equal to 708 kilogram meter per second. Since the man is brought to rest, it means the final momentum is 0. Since the final velocity is 0, so Pf is equal to m multiplied by the final velocity, which is 0. So the final momentum is 0. So it means the change in momentum, change in P, is equal to Pf minus Pi, and that's 0 minus 708, and that is minus, let me just 0 minus 708, and that is minus 708 kilogram meter per second. So that is the change in momentum. So we can now calculate the force on the man for both cases. The change in momentum is the same for both cases, but the force will be different since the time is different. So for the first one, F1 equals to change in momentum, which is minus 708 over the change in time, which is 0.01 seconds. Minus 708 divided by 0.01 seconds is 70,800 Newton minus 70,800 Newton. Wow, that's a huge force. Well, F2 is equal to minus 708 divided by 0.08 seconds, and that is equal to minus 8,850 Newton. Okay, now let us compare the two forces. But first of all, the negative sign means that the impulsive force exerted by the ground on the man acts upward. So the impulsive force acts upward on the man. The impulsive force is exerted by the ground on the man. So and the force acts upward, opposite to the direction of motion. So now let us compare the force. This one is 70,800 Newton. This one is 8,850 Newton. As you can see, when the time is delayed to 0.08 seconds, by landing with a cushioned or padded shoe, the force decreases to 8,350 Newton. So when the momentum changes very quickly, the force is large. That's the meaning. And when the momentum changes slowly, the force is small. So by increasing the time for a change in momentum can reduce the force. So it means it's not the change in momentum that is dangerous, it is how quickly the change occurs. How quickly the change occurs. Time. So that's for that other question. The main important thing you need to know is that by increasing the time of change in momentum, you can decrease the force. So that's it. The next thing is the application of Newton's second law. One application of Newton's second law is the Atwood machine. This machine consists of two bodies suspended by a rope passing over a frictionless fixed pulley. The two masses are m1 and m2. I want to derive the formula for the acceleration of this system. If m2 has the larger mass, when you release the rope, m2 will pull the system downward since it has the larger mass. So the direction of motion will be downward like this. Now for m2, two forces are acting on it. The downward force, which is the weight, and the upward force, which is the tension in the rope. The net force on m2 will be the difference between these two forces. Since m2 is moving downward, it means the weight is larger than the tension. So the net force on m2 will be the weight, which is m2g, minus the tension, equals to ma, which is the mass times acceleration, so m2a. So that's for this mass. For this also, two forces are acting on it. The weight, which is downward, and the tension, which is the upward. Now remember that if this is moving downward, this is moving upward. So it means the tension is greater than the weight of m1. So the net force on m1 will be the tension minus the weight, which is m1g, equals to m1a. So that's the net force for both of them. For this, weight is greater. So the net force is m2g minus the tension equals to m2a. For this, the tension is greater. So the net force is tension minus the weight downward force, which is m1g equals to m1a. So since the rope are connected, since the rope is connected, the tension is equal. Now we can make the tension the subject of the formula here and put it here. So the tension here is equal to m1a plus m1g. So you can replace the tension here with this. I just want to find the acceleration. So we have m2g minus into brackets m1a plus m1g equals to M2A. So we have M2G minus, open the bracket, minus M1A minus M1G equals to M2A. Now we can rearrange. Let us put it like terms. M2G minus M1G is equal to M2A plus M1A. So we can factorize, G is common to both of these, so we can factorize it out. G is equal to M2 minus M1 equals to, you can factorize A out. A is the same since they are connected to each other. So A M2 plus M1. We can make A the subject of the formula. So A will be equal to this G into bracket M2 minus M1 over M2 plus M1. So that is the formula for the acceleration of the system. G into bracket M2 minus M1 over M2 plus M1. If you know the mass of both of them, you can get the acceleration and the tension. So you can use any of this to get the tension. Just make T the soldier the formula and input the mass and the acceleration and the, so that's how to get it. Memorize this formula. A equals to G into bracket M2 minus M1 over M2 plus M1. That's the formula for the acceleration. So that's for the Atwood machine, an application of Newton's second law. Here is a question. A simple Atwood machine consists of two masses, 3 kg and 5 kg, connected by a string passing over a smooth pulley. Calculate the acceleration of the system and the tension in the string when the system is released. Now, let's draw the diagram. 5 kg, 80 kg. You can put the masses anywhere. So this is the 5 kg mass, this is the 3 kg mass. So we know the formula for acceleration already. A G M2 minus M1 over M2 plus M1. That's equal to 9.8 into bracket 5 minus 3 over 5 plus 3. 9.8 times 2 over 8 is 2.45 meter per seconds. Second square. That's the acceleration. Now, to calculate the tension, you can use any of the net force equation of this. You can use this, you can use this. So let us use this, the 5 kg mass. Since this is heavier than this, the direction of motion will be downwards like this. So this 5 kg mass will put it downward. So 2 forces are acting on it, on this 5 kg mass. The downward force, which is the weight, and the upward force, which is the tension. So since the weight is more than the tension, then the net force is M2G, which is the weight, minus the tension, equals to M2A. So that's the equation. If you want to use this, it will be T minus M1G equals to M1A. If this is moving down, this is moving up. So tension is more than the weight. So the difference of the forces will be the net force. So, but I want to use, let me use this. We can use either of them. Or let me use this second one. Let me use the second one. So T minus M1G, which is the weight, downward force, equals to M1A. So T equals to M1A plus M1G. M1 is 3. So 3 times 2.45 plus 3 times 9.8. 3 times 2.45 plus 3 times 9.8 is 36.75 Newton. So that's the tension in the string. So acceleration is 2.45 meter per second square, and the tension in the string is 36.75 Newton. So that's the end of this video. Thanks for watching.